Hey, I've been hearing a lot about microcomputer and interface technology lately. Can you break it down for me?
Sure, microcomputer technology revolves around the design, operation, and interaction of small computers that typically consist of a microprocessor, memory, and input/output interfaces. It all started with the advent of microprocessors, like the 8086, which laid the foundation for modern personal computers. What exactly would you like to dive into?
Let's start with the architecture of microcomputers. I've heard about the von Neumann architecture. What exactly does that mean?
The von Neumann architecture is a design where the computer's memory stores both data and program instructions. It uses a single bus for communication between the CPU, memory, and I/O devices, which makes it quite simple but also has limitations, like the bottleneck in data transfer between the CPU and memory. The alternative is the Harvard architecture, where the data and instructions are stored separately.
Right, so the von Neumann architecture has a single shared bus. But how does that affect performance?
Exactly. That shared bus can lead to a bottleneck, often called the von Neumann bottleneck. Since both program instructions and data are accessed through the same bus, the CPU has to wait for data to move in and out of memory, slowing down processing. That's why modern architectures like Harvard, or even more complex systems, have separate pathways for instructions and data to improve throughput.
Interesting. So how does the CPU fit into this whole picture? I've heard of 8086, 8088 processors. What's so special about them?
The 8086, 8088 processors were groundbreaking in the late 70s and early 80s. They're 16-bit processors, which means they process data in 16-bit chunks. But the 8088 version specifically has an 8-bit external bus. This was a cost-saving measure. The 8086 had a 16-bit bus that allowed it to move data faster. But the 8088 was designed to be compatible with the existing 8-bit buses of the time.
Ah, I see. So 8088 was like a more affordable version of the 8086. But how does the CPU interact with memory and peripherals?
Good question. The CPU communicates with memory and peripherals through a set of buses. The address bus determines where data should be read from or written to in memory, while the data bus carries the actual data. The control bus sends signals to manage the operations, telling the system when to read or write. These buses enable the CPU to fetch instructions from memory, execute them, and manage input/output devices.
Okay, so these buses are crucial. But let's talk about assembly language programming. How do you program an 8086 in assembly?
Assembly language for the 8086 is quite low level, closely aligned with machine code. You write instructions that directly correspond to the operations the CPU can execute, like moving data, performing arithmetic, or jumping to different parts of the program. It's a bit of a challenge because it requires managing registers, memory addresses, and knowing the CPU's instruction set intimately.
So it's like writing in a very direct language for the hardware. How do you manage things like loops or conditional statements in assembly?
In assembly, loops and conditionals are controlled using jump instructions. For example, a jump if equal instruction might check a condition and then jump to a different section of code if the condition is true. It's a bit manual compared to higher level languages, but it gives you fine-grained control over execution.
But what about input/output, I/O? How does the 8086 handle communication with external devices?
I/O in microcomputers can be handled in a few ways. The 8086 typically uses memory-mapped I/O, or isolated I/O. In memory-mapped I/O, peripherals are treated like memory locations, so you use the same instructions for accessing both memory and I/O devices. Isolated I/O, on the other hand, uses special instructions that distinguish I/O operations from memory operations.
I've also heard of interrupts. How do interrupts work in this context?
Interrupts are a way to temporarily halt the CPU's current operations and give priority to other tasks, like responding to I/O events. The 8086 has a vector table that maps interrupt numbers to specific service routines. The 8259A interrupt controller helps manage priorities when multiple interrupts happen at once, ensuring critical operations get attention first.
So the interrupt controller acts as a manager for which interrupt gets processed first?
Exactly. The 8259A can handle multiple interrupts, and its priority system ensures that higher priority interrupts are serviced before lower priority ones. This is crucial in real-time systems where timely responses are critical.
That makes sense. Now let's talk about those common interface chips like the 8255, 8253, and 8251. What's the role of the 8255?
The 8255 is a parallel I/O interface chip that allows the CPU to communicate with external peripherals. It has different modes of operation, like input mode, output mode, and bidirectional mode, making it very versatile. You can configure it for different kinds of devices, such as sensors or switches, by using these modes.
How does it handle parallel data? Does it just move bytes at a time?
Yes, it handles parallel data by managing multiple data lines simultaneously. It can send or receive multiple bits of data in parallel, which is much faster than serial communication, where data is sent bit by bit.
I see. And what about the 8253 or 8254? I've heard they're timer chips.
Yes, the 8253, 8254 are programmable interval timer chips. They are used to generate precise time delays or intervals. You can configure them to count events, generate clock signals, or even manage task scheduling in more complex systems.
So they're crucial for timing operations in a system. And what does the 8251A do?
The 8251A is a serial communication interface. It allows the CPU to communicate with devices using serial data transmission, which is more efficient over long distances compared to parallel communication. The 8251A supports both synchronous and asynchronous modes, making it very flexible.
That's pretty flexible. What's the difference between synchronous and asynchronous transmission?
In synchronous transmission, data is sent in a continuous stream, synchronized to a clock signal, ensuring both sender and receiver are in sync. Asynchronous transmission, on the other hand, sends data in chunks with start and stop bits, so no clock signal is needed, but it's less efficient and requires more overhead.
Got it. Now, I've also heard of buses like ISA and PCI. How do they fit into the picture?
Buses like ISA and PCI are used to connect the CPU to peripheral devices and memory. ISA, or Industry Standard Architecture, was common in early PCs and was quite simple. PCI, or Peripheral Component Interconnect, is a more advanced bus standard that supports faster data transfer and greater flexibility. It also allows peripherals to be connected without taking up precious CPU address space.
So PCI is more advanced. What about newer technologies like USB or SPI?
USB is a very common interface now. It's designed for hot swapping and easy peripheral connections like keyboards, mice, and external drives. SPI, Serial Peripheral Interface, is a faster, lower latency communication protocol, often used in embedded systems to communicate with sensors, memory chips, and displays.
Seems like the landscape has evolved a lot. Do you think there's a clear trend towards serial interfaces over parallel ones?
Yes, absolutely. Serial interfaces are becoming more popular because they're simpler to implement and can transmit data over longer distances with fewer signal integrity issues. In contrast, parallel interfaces can suffer from issues like crosstalk and signal degradation, especially as the data rate increases.
That makes sense. Do you think we're heading towards a more universal, unified interface standard in the future?
I believe so. USB has already made a huge impact in terms of standardizing connectivity. There are also emerging standards like Thunderbolt, which can handle both data and power over a single cable. We might see more universal standards as technology continues to converge.
Great insights. Thanks for breaking all this down for me.
Anytime. It was fun diving into this. Let me know if you have more questions in the future.
Actually, I do have one more question. With all these advancements in interface technologies, do you think there's still a place for older technologies like ISA or even 8255 chips in modern systems?
That's an interesting question. While technologies like ISA and the 8255 might seem outdated, they're still useful in some niche applications, particularly in legacy systems or very specific industrial settings where cost and simplicity are key factors. For instance, the 8255 is still useful in embedded systems that don't need high-speed data processing, but it's true that newer chips with faster interfaces like I2C or SPI have largely replaced it in modern designs.
I see. So for high-performance systems, newer chips are the go-to, but for simpler, cost-sensitive applications, older ones still hold value?
Exactly. It's all about the use case. Modern systems with high throughput requirements demand faster, more reliable interfaces like PCIe, USB, or Thunderbolt. But for simple control systems or low-cost devices, older chips like the 8255 can still get the job done without the complexity of modern interfaces.
Makes sense. Speaking of modern interfaces, do you think we're going to see any significant shifts in terms of speed and power efficiency in the next decade?
Definitely. Speed and power efficiency will continue to be major focus areas. As more devices become interconnected in IoT networks, minimizing power consumption will be critical. We're already seeing more emphasis on low-power communication standards like LoRaWAN, Zigbee, and Bluetooth Low Energy, BLE. For speed, the push towards 5Gs and even beyond, with technologies like 6G, will likely drive even faster data transfer rates, especially for wireless communication.
That's really fascinating. And what about the rise of quantum computing? Could that disrupt current interface technologies?
Quantum computing is definitely a game changer in terms of computing power. But for now, it's still in its early stages. Quantum computers operate fundamentally differently from classical computers, so they would likely require entirely new interfaces and communication protocols to interact with classical systems. It's unlikely to disrupt current microcomputer interfaces in the near term, but it's something to keep an eye on in the long term.
Right, so for now, the focus will remain on optimizing classical systems. What do you think the next big breakthrough in microcomputer interfaces will be?
I think we're going to see further integration of systems. For example, systems like USB-C, which combines power, data, and display in one interface, are paving the way for even more versatile solutions. Additionally, there's a lot of excitement around the potential of optical interconnects, which could revolutionize speed and bandwidth. So, expect to see more hybrid systems that provide seamless connectivity across different types of devices.
Optical interconnects? That sounds interesting. How would they work in practice?
Optical interconnects use light to transfer data instead of electrical signals. This could dramatically increase the speed of data transmission, reduce latency, and eliminate many of the limitations of copper-based connections. In practice, optical interconnects could replace traditional copper wires in applications like data centers or high-speed networking, providing much higher bandwidth and lower power consumption.
That sounds like a real leap forward. How close are we to seeing these optical interconnects become mainstream?
We're not quite there yet, but there's a lot of research being done, particularly in the field of photonic integrated circuits. Some companies are already experimenting with optical interconnects for short-range data transmission, especially within data centers. It's still a few years away from being mainstream, but we might start seeing it in specific applications sooner rather than later.
I'm excited to see how this develops. Now, going back to assembly programming for a moment, do you think assembly language will eventually be phased out as hardware becomes more complex?
Not entirely. At least not in the foreseeable future. While higher-level languages have made it much easier to program, assembly still gives developers precise control over hardware. In specialized fields, like embedded systems, real-time applications, or performance-critical applications, assembly programming is still valuable. It's unlikely to be phased out, but its use might become more niche.
That's good to know. So it's still an important skill to have for certain use cases, but not the go-to for most general-purpose development?
Exactly. If you're working on hardware-level development, embedded systems, or optimizing performance, knowing assembly can be a huge advantage. But for everyday application development, higher-level languages are more efficient and easier to manage.
Got it. As technology evolves, it seems like the focus is shifting more towards simplicity and higher-level tools. But there's still room for deep, low-level control when needed.
That's right. The trade-off between control and convenience is always there. Higher-level languages provide more abstraction and faster development cycles. But sometimes that comes at the cost of performance or the ability to interact with hardware at a deep level. It's all about finding the right balance for the task at hand.
I can see that. It's like having the best tool for the job depending on the situation. I really appreciate all this insight. You've made a complex topic a lot more understandable.
I'm glad I could help. It's always a pleasure to discuss these topics in depth. Let me know if you ever want to dive into anything else.